Let's get started. So thanks for coming, everyone. My name is Virajit, and this is Chris. Today, we're going to talk about our proposal for implementing tiering in HDFS by building on its support for heterogeneous storage. Sorry. OK. So both of us are from the Microsoft Cloud and Information Services Lab, or CISL, which is an applied research group. We are partly based out of here, and some of us are in Redmond. We do research and development in large-scale systems and machine learning, and we build prototypes, research prototypes, publish a lot of papers, and also write code for production clusters in Microsoft. For people around here, the more relevant thing is a lot of the members in our group do a lot of contributions to open source. There were a lot of contributions to Apache Hadoop Yarn, and also Apache Reef was born out of CISL, which is like a standard lib for resource management frameworks like Yarn and Mesos. So over the past few years, Hadoop has gained a lot of traction, and one of the main reasons is that it gives you the ability to place data in one single place in HDFS, and it gives you a set of common formats and abstractions that you can use to query and query data and also write data too. Now the data is protected and managed by a set of user-defined and operator-defined invariants, such as you can enforce quotas, you can enforce user permissions, and also encrypt data, and also have the ability to spread data across the heterogeneous storage media in your clusters. Now, this is all fine, and it works very well if you have only one cluster that you operate, and one cluster alone holds your data. But in most practical cases, many companies, big or small, have data spread across multiple clusters. For example, you would have different clusters for production use and for research and testing use. And also because of, say, privacy or compliance issues, you would want to run different clusters. And some of the data sets might be actually shared across these clusters, while some might have to reside only in those in a particular cluster. Also, in cases where you're trying to do cloud backup or disaster recovery or BCP, your data would actually be in clusters that might be completely in different geographical locations, and they might be running completely different software stacks. For example, your on-prem cluster might run HDFS, but your cloud backed up data might be backed up on Windows blob storage, which is a completely different software stack. And also, most clusters today come with heterogeneous storage media. So you have your main memory, you have your SSDs and disk, and for performance, and if you would want to use these different storage media in a performant manner so that your applications run very well. So in most cases today, these multiple clusters are managed by two common techniques. The first one is to use the framework itself. So this is, the example of this scenario is something like diskcp, where you would copy data from one HDFS cluster to another HDFS cluster. This is nice because the clients can process data locally, and there's no visible intermediate state left by when you run a diskcp job. However, this uses up compute resources, and if you're copying large amounts of data and using up a lot of compute resources, you would have to plan this properly so that it does not interfere with the regular cluster operations. The second technique is to use the application itself. So here you have to make the application aware that the data is actually stored in multiple clusters. So the application has to explicitly read data from multiple clusters, it has to manage things like permissions, and has to authenticate to multiple clusters. So this is good. The application itself can enforce its own consistency model, but this is generally hard to do, and every application has to implement this. So as opposed to these two techniques, what we are proposing is to use the platform to manage multiple clusters. In particular, we are saying that you would want to use a storage layer to manage your storage clusters. So this allows users and applications to have transparent access to multiple storage clusters, and also have a single unified namespace across these clusters. And this also gives you opportunities to improve application performance by caching data in your local cluster instead of actually having to go every time to a remote cluster and read data. And you can also do fancy things like prefetching, where if you know that a job is going to run at some point of time, you can get the data into your cluster ahead of time, and the job will run faster. The harder thing to solve here is consistency, which we'll get to later in the talk. So this talk is about how we are going to enable this tiering in HDFS so that HDFS can be used as a front end to access data in multiple back-end storage clusters. So this brings along with itself some of the nice properties that HDFS has, such as enforcing security, encrypting data, and enforcing user quotas, and so on. Now, there are several challenges that we need to solve before we can actually make this practical. First of all, we need to be able to synchronize the metadata without having to move the data around. You don't want to be copying data around. It end up being very inefficient. And so you would want to dynamically page in data that's only accessed. And for example, if you have lots of data in the cloud, but only want to work with a subset of the data, you only want to bring that data in when it's actually accessed. And we also need to define policies on when you can prefetch data, and when the local cluster is nearing its utilization cap, you would want to evict local data so that you have more space for new data. And also, in the case we're trying to solve, the backing store or the external store might change because you have other applications or other clusters reading or writing to it. So we would want to mirror these changes in your front-end HDFS cluster, and we would want to do them intelligently so that we are not wasting data. So for example, if you cached a particular file, but it has been renamed in the backend, you can still retain the data for this file and don't have to evict it. And also, we would have to handle writes consistently. So if you have writes going to your backing store from two different clusters, you have to make sure that the writes can be merged properly so that in the end, the state of the external store makes sense. So the way we are proposing to do this is by introducing a new storage type in HDFS, which we call as provided. So this will be a peer to the existing storage types, which are RAM, SSD, and disk. So the data nodes would look something like this. So each data node can now have up to 4 different types of media. So in HDFS, you have the name node, which is divided into two parts. You have one is the name system, and the second one is a block manager. So the name system maps files to a set of blocks, and the block manager in turn manages the life cycle of these blocks, which includes maintaining state for where the replicas for these blocks are in the set of data nodes that the name node is aware of. Following the same thing, all provided files will also be mapped to blocks in the cluster, and these blocks will initially point to the provided storage type as being the location for the blocks. Now, you would need somehow to map these blocks to data in the backend. So the backend doesn't know about HDFS blocks. So we do this by maintaining what we call as block aliases. So block aliases are a simple tuple where you have a reference that can be resolved in the external file system or the external backing store, and a nonce, which is used to determine if the data that you are pointing to with the reference is the same as what you think it is, or if it has changed since the last time you have looked at this data. In a simple case where the backing system is a file system, the reference can be a simple tuple of the file URI, the length, and the offset of the file. This mapping from the blocks to the aliases is stored in a block map, which is accessible by both the name node and the data node, so that everyone can refer to it. Simply, you can have it, say, in a shared key value store, and both data nodes and name nodes should be able to read and write to this block to this key value store. So finally, we have in the data nodes what we call as provided volumes. So if anyone familiar with the implementation, data nodes has these volumes which hold the actual data. So this would be an instantiation of that volume, and so these volumes would be used to eventually write and read data from the external store. So you can think of the provided volume as being a client to the external store that understands how to address data there. So looking at a simple example to how this actually works, suppose you have data backed up in a cloud store, say Windows Azure's blob storage, and there's a certain namespace that is associated with this data. Now you would want to mount some portion of it in your HDFS cluster. When the mount process succeeds, it essentially means that we would like to access the data in the backing store from HDFS. So when a client comes up and it reads the data corresponding to a particular file from HDFS, HDFS should be able to understand that this file actually belongs to this external store, and it should be able to fetch data from the store and send it back to the client. Now, so I'm going to hand it over to Chris, who's going to develop more in deeper of how the provided storage type actually works in this example.
Please hear me? Okay. So drilling down into this example. So let's assume we want to mount this external namespace in HDFS, or rather just this subtree. So one way to think about this is we could generate a mirror of that namespace as a FS image, where the FS image is a checkpoint of the name node state. And so that stores all of the inodes, the structure of those inodes, all of the metadata about the inodes, and then for every file, the sequence of block IDs that are associated with it. And so for every file that we find in this external namespace, we partition it into logical blocks and store the reference in the block map with the corresponding nonce, because we need to be able to verify when we reference it later that this is the same data that we imaged in the first place. And so note that the image contains only the block IDs and the storage policies that we're trying to enforce, while the block map only stores the block. So if CDE were like a gigabyte or something like that, so the image could record I don't know, 4 logical blocks, and for each block, the block map would record the reference, the URI, offset length of the original file, and the nonce, inode ID, last modified time, again, whatever is sufficient to detect inconsistency. So a quick note on block reports, if anyone's familiar with them. And by the way, if anyone is unfamiliar with any of these, please speak up. It's fine to be interactive on this. The name node persists metadata about blocks, but their location in the cluster is reported by data nodes. So every data node reports all of the volumes that are attached to it, all of the hard drives, SSDs, things like that, and a list of all of the block IDs that are stored, that are present in each storage. And so the name node knows all of the blocks that are addressable by that node and in what media they're stored. And so when the name node starts up, it comes out of safe mode and starts forward operation and accepting writes when some fraction of its namespace is available. And so when a data node reports its provided storage, it doesn't send a full block report, right? This would be redundant. But recall it's a peer of all of the local media on that data node. It only reports that any block stored inside of a ID matching that provided storage is reachable through that node. As long as the name node has at least one data node reporting that provided storage, it considers all of the blocks that are in the block map as reachable, because any one of those nodes can proxy the request back to the external store. The name node, when it starts up, scans the block map to discover all of the blocks that are part of the provided storage. This is in contrast to I don't know if anyone's familiar with the read-only shared replicas. That's a slightly different approach where all of the blocks might be resident on a filer, and then every data node would mount that filer locally. And so they would all redundantly report all of the blocks to the name node. Instead, we just report like it's addressable, and the name node figures out what they mean. And so we only scan it once. So inside of the name node, we relaxed another invariant, an assumption that every storage, every hard drive and SSD belongs to only one data node, because in our case, it belongs to multiple data nodes. So when a client requests the block locations for a file, here Z1, the name node will report all of the local replicas, and the name node will select a single provided replica. So of all of the data nodes where it's addressable, it'll pick one, say like closest to the client. You can implement a lot of policies here, but the closest to the client makes the most sense, right? It's the fewest number of network trips. So this, again, avoids every data node in the cluster as a valid target for the, which is accurate but not particularly helpful for applications, particularly in large clusters. So when the client requests the provided block from the data node looks at the block in the block map. It'll find the block alias and resolve the reference. Request the block data from the external store. Return data to the client having verified the nonce. Right? This is where we prevent ourselves from returning valid information. And because the block is read through the data node, we can also cache the data as a local block and avoid reading it multiple times as we might if we were doing like a client-side mount table. So there are a few points that out here. First, this is a pretty small change to HDFS. The only client visible change adds this new storage type, which very few applications even pay attention to. And so as a user, interacting with this data is a lot simpler than coordinating with other copying jobs or other methods you might use to synchronize your data into the local cluster and share it with other people who might be accessing it concurrently. And so to take our cloud example, all of the cluster's data is immediately available once the namespace loads and data nodes start coming online. Even if the replication policy hasn't prefetched all of the data into local media, right? And so this means that if you bring up your cloud instance that includes the FS image that you generated from your external store, you can start applications. They can start immediately working on data as it's copying that data into local media. And so for S3 or Azure or places where you might be throttled, the HDFS can do some intelligent prefetching to move that data inside of your VM so that you are no longer, so that you aren't subject to that constraint. Second thing to note is that particularly for read-only mounts, this is a pretty narrow API. For if you consider cloud backup scenarios where the name node might be the only writer to the namespace, then we really only need the block to object ID map, and then we don't even have a namespace to synchronize with. We only need to persist the name node image, which we should be protecting anyway. And from that, we can bring up any prefix of its log with all of the block data that have been persisted in the cloud store. Right? Third thing to notice is another note on caching is that the name node doesn't necessarily need to pick the replica that's the provided storage that is closest to the client. If the name node wants to add a replica at some other point in the cluster, but only read through once, then it can instruct the client to read from the target data node, and and as it's reading it through, the data node will automatically store a copy in local media, right? So we can avoid redundantly moving some data across the cluster. This also works, by the way, without provided storage in the picture. Like if you imagine an environment like HBase where data are moved by rewriting them, it might be more efficient to read through into a storage local to that daemon, or the region server. Finally, for cloud scenarios, the cloud credentials are hidden from the client in both S3 and Azure Storage. Both systems authenticate clients to containers using a single key. So all of the users in the cluster are getting a polite hint of what their permissions are, but they aren't actually enforced, right? And so by pushing this behind, and so because HDFS owns and protects the external source credentials because they're part of the platform, they're part of the data, you deploy Kerberos inside of your cluster, have excuse me. You can have HDFS authenticate all of your users, and you can prevent that secret from leaking into. So this is pretty straightforward for read-only cases, but to emphasize it's imperative we never return the wrong data. So if a file were overwritten in the backing store, we should never return part of the previous file and part of the second. And this is why we include the nonce with the block alias. But there needs to be another HDFS. If our external store has a namespace that's compatible with the Apache Hadoop file system API, then we can always scan, but while refresh is limited to scanning, the view to the client may be inconsistent. So if the client may see some unpromoted, like if you consider the end of a job, the client may see some unpromoted output, some output, and a Sentinel file that declares that everything has been fully promoted. And this is just an artifact of the order in which the name node happened to have scanned those files. Better cooperation with some of the external stores can tighten the namespace integration to expose meaningful states. So by way of example, if the external store supports snapshots, then HDFS could move from one to the next, maintaining a read-only version of the previous snapshot while it updates. It can atomically move to the next stage and then inform the external store that it no longer needs that snapshot. Or alternatively, the external store can declare a sequence of snapshots that are semantically meaningful that the name node that can move between. For anyone familiar with like Corfu or Tango, this is work out of Microsoft Research with Dalia Maliki, Mahesh Radhakrishnan, or with WANDisco's Paxos engine. We can make the metadata synchronization really tight and meaningful, but we still need the logic, the block layer that we're adding as provided storage. So no matter how tight we make the metadata synchronization, we still need the full wire up. And in addition to correctness, as Virajit mentioned earlier, we also need to be mindful of efficiency. And so a lot of output in HDFS is promoted by renaming it. And if the name node were to interpret that as a deletion of the file and a recreation of it, then the HDFS cluster would start to discard blocks just to recopy them again, exactly at the moment when another job is likely to pick them up and consume them. So one of the other goals of this project is to conservatively identify those cases based on actual workloads, right? And so we don't want to scan, when we do a scan, we don't want to consider, the full set of, we don't want to consider that the file could have moved anywhere in the namespace. That doesn't happen in practice. We assume they would be renamed like within a parent or something like that. And so those are cases we can detect and avoid redundantly copying data. And since I mentioned some of these strong consensus engines, this isn't a real shared namespace, right? Like even the read-only case is eventually consistent. In the base case, we're scanning the entire subtree of the external store, and that's obviously not workable. But again, most big data workloads don't hit any of these pathological cases. The typical year, month, day, hour kind of layouts are that are common to these analytics clusters are mostly additive. And even the simple techniques that we're proposing for some of the early iterations of this work are entirely sufficient for that case. Other thing to note is when writes conflict, there's only so much the file system can do to merge conflicts. And let's set aside really complicated cases like compactions. Even simple cases may not merge cleanly. So if you get to like the simplest possible case where a user creates a directory that is also present in the external store, and both of them are empty. Can you merge that? Maybe not. I mean, successful creation might be gating access. There are a lot of frameworks in the Hadoop ecosystem that follow conventions that rely on the atomicity of operations in HDFS. So if you successfully create a directory, that means you should subsequently take an action, and the file system wouldn't know to roll back the consequences of the successful operation if it were to do a merge. And this is even ignoring the fact that there is no correct answer for the merged result. If the permissions, timestamps, storage policy, there's a bunch of other metadata that may not match, and it's not clear that there's a correct answer for the file system without knowing the application semantics. Where we can inject the application semantics, we might be able to do a little more there, but in the general case, we're assuming that by construction, most clusters are going to be either producers or consumers for some part of the shared namespace. And given the workloads that we've been looking at, that's not an unreasonable assumption. And so fundamentally, there's no magic here. We haven't made any breakthroughs in consensus, but provided storage is a tractable solution that happens to cover some common cases in deployment in its early incarnations. And from a research and development perspective, there's some interesting problems in the policy space, particularly related to prefetching work and eviction. And yeah, please find us after the talk to talk about that area. It's something that we're really interested in. And yeah, the implementation. So we're going to have to do this in a staged way. The read-only case is pretty straightforward. We implemented a proof of concept inside of a few weeks, spread out over a while. And we have a link to that on the Jira. We can start with the name node just managing an external store. This is following the flow we talked about earlier, where we generate an image, bring up a name node, and it is responsible for the external store. This lets us defer some of the mounting logic, which would otherwise interfere with the name node operation. And when we explore strategies for creating and maintaining mounts in the primary name node alongside other data, we're going to have to reconcile what we're doing with the name node locking, and it's a formidable challenge to relax that. We're slightly encouraged in this because most of the invariants that we might enforce using the strict locking inside of HDFS, the atomicity of renames, quotas, things like that, don't really apply once you're inside of the mount, right? And so we believe we will be able to separate most of the locking without too many weird artifacts. Refresh, we're going to start with naive scans and then improve. Identifying the subtrees that change frequently, are accessed frequently, these will be the ones that we're going to want to scan more often. This kind of improves the general case, but polling is fundamentally limited. We want to move pretty quickly, given some experience running some of the early versions of this, to recognize the common abstractions when tiering over stores that provide version information, snapshots, access to their log, things like that. And we want to be able to get some tighter integrations for refresh. Writes are complex. Those are hard. And so we'll move from working system to working system by first wiring in the provided type into the state machines inside of the data node. And so then the write-through case is tracked up, particularly when the external store is an object store or something like that. This is the standard cloud backup kind of scenario. And ultimately, we'd like to use local storage to batch or even prioritize these transfers between HDFS and the external store, whether it's a cloud storage engine, another instance of HDFS, et cetera. And because HDFS sits between the client and the external store, if we want to solve problems like limited bandwidth, how do we prioritize which transfers have a waiting reader for them versus other reads to the external store that might just be trying to bring in some local replicas for to optimize future jobs, like prioritizing those writes across each other and figuring out which media to store them in and where in the cluster to store them is what we consider the interesting part of this problem and the ongoing work. So we're doing everything in Apache. Please join us. We have a design document posted to Jira, and including some of the active discussion of implementation choices, and we'll be starting a branch inside of Apache to host these changes. I also think the design document for read-only shared replicas is superlative, and so if you want to contribute, but you are looking for some orientation, particularly in the internal details of the data node and things like that, I would recommend that reading. And so, yeah, it looks like we have a few minutes for questions. But generally, just please find us after the talk. There are far more details than we can cover in a single presentation, and we're still setting the design. So it's a time when we're very open to collaboration. So yeah, thanks. Let's take a couple questions. So the data node retrieves the data by instantiating a client for the external store, right? And so by way of example, to take our cloud scenario again, if we receive a request for a block, that block is mapped to some region in the original store. And so we need to create a client for that, say, an Azure S3 instance that would then go back to the external store, authenticate using the credentials that are embedded in the data node, and pull the bytes that correspond to the region that was identified in the image. And it would decide whether it wants to tee that into local media while it also returns it to the client, or just pipe it directly to the client. And from the client's perspective, they're just performing a standard DFS read. Any other questions? Yeah.
You talk about intelligent prefetch.
Yeah.
How does name node know when to prefetch?
That's a great question. So the question was, where do you start to put the prefetching policies? Some of our related work is in planning pipelines and being able to move workloads between when data become available and when the computation needs to end. And so if we have some hints from that system on which data are going to be read, then we can not only prefetch data knowing when they're placed, but we also might be able to affect the placement of those pipelines given some constraint. For example, if I have limited bandwidth going back and I have to run 3 pipelines, then I may need to move one of them in order to compensate for that constraint, right? And so we knew we can use some additional metadata, but we're also looking at, for just without any tuning, we're looking at the efficacy of standard caching techniques. We're looking at, for real workloads, how well does LRU work, how LRUK, ARC, things like that. Yeah. How does it work with encryption? So you could do it a few ways, right? You could either use the API in HDFS to copy the encrypted data directly to the backing store if, for example, you don't trust it, right? If you're purely using it for backup and you keep backups of all of your keys somewhere else with your metadata and things like that, then for the pure backup solution, then yeah, you can just copy the encrypted data back. Otherwise, you would need to impersonate the client, decrypt the data, and then write it back using whatever your backing store supports. But because it's part of the deployment, it's probably the right place to put those knobs, right? Because if you have some data that sits under some part of the namespace that, for example, should never leave that cluster, then that's an invariant that you can enforce. Because, again, it's all inside of HDFS. Oh, you've made me so happy. We even have a slide. So yes, there are a few challenges if you have a client-driven approach, especially if you want to keep like multiple stores kind of consistent with each other. One of them is that if you have a partially successful operation, you'd need another client to be able to discover your intention and finish that operation if the first client died. Right. You also have the classic problem of UFS, which is that if you and I have different mount tables, then I can't give you a reference that you can resolve, right? Because I might have a different mapping for that prefix inside of that cluster. And so by putting it all under a single namespace, we get a semi-consistent view. Well, we get a consistent view from the perspective of HDFS. And HDFS also defines the ordering of all of the operations that we're doing in the backing store, assuming that it's mounted for write, right? So the other thing is that if you want to start implementing a system that's able to like dynamically page in data, you need to write things like quotas. You need to figure out how to move data between storage tiers. You need to duplicate a lot. Well, you not only need to duplicate a lot of the logic that's already in HDFS, but you have to be consistent with the logic that's already in HDFS. And so if you have a quota of SSD inside of some subdirectory in HDFS, and you've requested some external service to copy your data into it, then the two need to match up. And instead, if you just use the single mechanism that's already part of your platform, you don't have those mismatches. Or other reasons. Oh, yeah. You also need to, as part of clients completing others' operations, many operations like chmod is a pretty straightforward one that other clients by definition can't either roll back or they may not be able to roll forward in some of the other clusters you're trying to keep consistent. Whereas again, if it's all inside of HDFS using inside the platform, then by definition you have enough privileges to be able to bring the namespace to a consistent state, especially if you have a well-defined contract where you're saying, look, I will consider the remote authoritative, so if someone creates a file in this cluster that doesn't exist in the other cluster, I'll get rid of it, or vice versa. If I have something in the remote cluster, I consider myself authoritative and I can replace it, and then this gets into the complexity of merging, right? Like, what do you do if you detect a conflict? And that's an open question. I mean, what analogous stores do, like if you look at like Dropbox or OneDrive or something like that, they might rename one with the name of the host or something like that, and then just throw up their hands and say like something happened. And that's probably the most that the file system can do. But again, in some application scenarios, you may be able to make more aggressive assumptions because it's under management of some other system, right? Oh yeah, sorry.
My question is around is there anything special about provided replicas with respect to the corruption of replicas? Like, is there anything special that we do for corrupt replica map data structure since we're doing something with the blocks map and we want to work with people?
That's an excellent question because we aren't getting, for example, like reports from the external store that confirm that those data are still valid, right? And unless we were to read them or be able to trigger a report on the remote, we don't know if those data are scrubbed. We don't know what the contract is. And so especially if I had 2 HDFS clusters and I wanted to, let's say, drop the replication in one of them down to 1 because I knew another cluster had 3 replicas or something like that. Specifying that in a policy is not straightforward. We could invent a mapping that would be something like, well, if I have 4 replicas and my storage policy does store the first one in disk and the other 3 in provided, then I might be able to interpret that as set the replication on the remote to be 3, right? That's a little wonky. We aren't sure what the right semantics for that would be, but in most of the scenarios we're looking at, the external is at least as durable as HDFS, especially in cloud scenarios where we're deploying in VMs that may be preempted at any time. It's definitely more durable than HDFS. But for cases where it's not, it's unclear what the right semantics are. Any other questions? Going once, going twice. All right. Thank you.